Good evening. So now that we finished the discussion about vector spaces and bases, let's come back to the notion of eigenvectors and eigenvalues. And let's see that in fact, when we solve for the eigenvectors, right? So when we find each eigenvalue and then we try to find the eigenvector, we shall notice that in fact, as you remember already, there are infinitely many eigenvectors, because when we're actually looking for non-zero solutions, right, non-zero eigenvectors, it turns out that automatically the system that solves for them will give you infinitely many solutions. But moreover, these eigenvectors, all of them corresponding to an eigenvalue, they actually form a subspace. And that's actually easy to see. So remember, when you have the characteristic equation, your square matrix, right? So let's say n is an n by n matrix. And then you set it's equal to 0, and then you find lambda 1, lambda 2. Usually you have more than, depending on the case, you can have more than one eigenvalue. And then remember that for each lambda, for each eigenvalue, you're gonna find v, that is to say a non-zero v, right, such that a minus lambda in v is equal to 0. So in other words, you solve for each lambda, you solve the homogeneous system, a linear system given by this matrix, A minus lambda in. This always has infinitely many solutions, and that's a direct consequence of the fact that this determinant is equal to 0. So the columns or the rows are dependent. But it is also easy to see that it forms a vector space or a subspace, right? So given v1 and v2, two solutions of this linear system, notice that if I actually plug in a linear combination of these solutions, C1v1 plus C2v2, using the fact that matrix multiplication is distributive to the left, I can regroup these terms and distribute that matrix multiplication like so. And because again, I chose v1 and v2 to be solutions of that linear system, then each of these parentheses is equal to 0. So that means this is actually C1, each of these matrix multiplication is 0. So that means all I end up with here is C1 0, C2 0, which is equal to the 0 vector. So the main remark and the point of this last piece of the course is that for each lambda, the eigenvectors corresponding to lambda form a subspace, which is also called an eigenspace. So basically, when the succession, the mechanics on dealing with these quantities are like this. One finds lambda, then one solves for v, right, from that solutions, and then what we provide as eigenvectors, we actually provide the basis of the eigenspace, right? If the basis of the eigenspace has only one vector, then you usually basically, that's why you just end up, providing just one non-zero vector. So let's go back to the 2 by 2 examples that similar to the one we've done before, and then we can illustrate how this looks in for higher matrices like 3 by 3 or larger matrices. So let's say my matrix to begin with is given by the components 0, 1, -2, and 3. Okay, so the characteristic equation, let's subtract lambda from the main diagonal, is this determinant equal to 0. We're going to multiply the diagonals. So that gives me lambda squared minus 3 lambda plus 2 equals 0. Lambda 1 equals 1, lambda 2 equals 2, right? Because this factors nicely into lambda minus 1, lambda minus 2 equals 0. So why did I say that in this case? I said, well, to give me the eigenvector, you just provide the eigenvalue, provide just a non-zero solution of the following system. So let's start with lambda 1 equals 1. So again, let's formalize it. That's the goal of the discussion right now. Okay, so subtract 1 from the main diagonal, right? So it's minus 1, 1, negative 2, 3 minus 1, which is 2. So again, let's solve this formally, right? We set it's equal to 0, 0. Or we can just start, look, because this is the 0 on the right hand side. When we solve for v1 and v2, we can just only track the matrix itself, right? And then find its row reduced echelon form. We can multiply this by negative 1, the first row, then multiply by negative 2 and add it to the second row, which gives me 0, 0. So because we have only one pivot column, obviously we're going to solve for v1 in terms of v2. So v1 minus v2 equals 0, v1 equals v2, v2 is arbitrary, so let's call it r, some parameter. And so therefore the solution that provides me the eigenvectors is of the form RR, right? So because v1 is equal to v2. And so when I said just give me a non-zero, value, the easiest one you can find with like 1, 1, it's another way of saying that I want you to provide essentially a basis of the eigenspace. So this set of column matrices, right, with R any real number not equal to 0, any non-zero real number. So this solution, well, together with 0, 0 will form a subspace, let's put it this way. Okay, so 0, 0 obviously satisfies the solution of the system. So let's actually include that, because if I want to say it is a subspace, it has to have a 0 vector. So RR, including the 0, 0, forms a subspace, which is the eigenspace. And if you want to provide its basis, all you have to do is to write it as a linear combination of the independent vectors. Now the number of arbitrary constants indicates the dimension of the eigenspace, right? Because using scalar multiplication, you can say that any vector, any eigenvector in this eigenspace can be written as a linear combination of 1, 1. So on this basis, no pun intended, we provide as the eigenvector corresponding to lambda 1, 1. So when we write lambda 1 equals 1, and then v1 equals the vector, v1 bar equals the vector 1, 1, we provide essentially a basis of the eigenspace corresponding to lambda 1. And of course, we repeat the procedure for the other, for the other eigenvalue. Let's say take lambda 2 equals 2, subtract 2 from the main diagonal, that's negative 2, 1, negative 2, and 1 again. Let's not delve into the row reduced echelon form because it's just 2 by 2 again, so we solve essentially for one in terms of the other. So I'm going to get v2 in terms of v1, and I'm going to choose v1 to be r, an arbitrary constant. So how does the eigenspace look like? It is made of all the vectors of the form r to r, and again just only one arbitrary arbitrary constant, so therefore dimension is 1, and the basis of the eigenspace is again 1, given by 1 and 2, right? So therefore corresponding to lambda 2 equals 2, the basis of the eigenspace is 1, 2. Okay, so when the basis is just 1, made of one vector, it's pretty clear. Again, that's the main idea. In the 2 by 2 case, not always, but most of the time you have essentially dimension 1. The larger the matrix is, the more combinations you can have. So let's finish up the discussion with examples where eigenvectors, or eigenspaces have a higher dimension, like 2, for example. So let's stay tuned for the next page. All right, so let's take a 3 by 3 matrix. Now, because the characteristic equation is much harder to solve in general for larger matrices, we'll choose examples where it is actually easy to do. Okay, so let's take the matrix 2, 1, 0, 0, 2, 0, and 0, 0, 3. And by the way, when you have actually diagonal matrices, so when you have zeros below or above the main diagonal, as it turns out, eigenvalues are the entries on the main diagonal. And if you think of a cofactor expansion, that's easy to see, right? So let's look at the characteristic equation. So 2 minus lambda 1, 0, 0, 2 minus lambda 0, and 0, 0, 3 minus lambda. So I can choose, obviously, the first column in the cofactor expansion. So 2 minus lambda minus 1 to the 1 plus 1 is actually 0, is 2, so it's plus 1. Cross out row and the column. You're left. So the idea is that when you cross out the first and the last column, what's left is again a diagonal matrix. So you can continue with the cofactor expansion by the first column until you're left with the last entry on the diagonal. So when you look for the, so basically if you do the cofactor expansion by the first column in a diagonal matrix, you basically end up with the determinant being the product of the elements on the main diagonal, which means that when I set is equal to 0, the eigenvalues will be exactly the entries with some multiplicity, maybe like 2 appears twice in this case, right? So we have 2 eigenvalues, 2 and 3, right? The entries on the main diagonal. So let's compute the eigenspace corresponding to each eigenvalue. So if lambda 1 equals 2, we're going to subtract 2 from the main diagonal. So 0, 1, 0, 0, 0, 0, 0, 0, 1. And notice that is already in reduced row echelon form. We have 2 pivot columns, meaning that there is only one arbitrary constant. So I know already the eigenspace in this particular case is going to be again of dimension 1. So remember, basically we're solving for this system, right? v1, v2, v3, right? The eigenvector equal to 0. So pivot columns are corresponding to v2 and v3, meaning that v2 equals 0, v3 equals 0, and then v1 is left to be arbitrary. So again, we have dimension 1 for the eigenspace. Eigenspace is represented by the vectors r0, 0, and if I write it as a linear combination, 1, 0, 0 as a vector is the basis of the eigenspace, right? Which is the default choice, remember, as an eigenvector. And I think for this matrix, the same happens with the second eigenvalue. So we're going to do another one in which actually you have, because I already promised you, right, that you have other dimensions. So let's actually finish this one. Lambda 2 equals 3. Subtract 3 from the diagonal. Let's see, 2 minus 3 is negative 1, 1, 0. 0, 2 minus 3, which is negative 1, 0. 0, 3 minus 3 is 0. Let's do the reduced row echelon form. 1 minus 1, 0. We just multiply by negative 1. And then add row 2 to the row 1. I could have done this in one step actually. Again, we have 2 pivot columns corresponding to v1 and v2. So v1 equals v2 equals 0, and this time now v3 is arbitrary. Again, let's call it r. So now my eigenvector, a typical eigenvector, is 0, 0, r. With the basis 0, 0, 1. Okay, so that's the basis of the eigenspace. So this matrix had 2 eigenvalues, and their corresponding eigenspace at dimension 1. All right, so let's finish up with examples in which dimension is not 1. Again, just a simple matrix so that it's easy to compute. So let's say we have 2, 0, 0, 0, 2, 0, 0, 0, 3. Again, notice it's diagonal, so I know already the eigenvalues are 1, 2, and 3 like before. And starting with lambda 1 equals 2, subtract 2 from the main diagonal. These are kind of trivial examples, but again, if they're not, it's just too tedious to compute by hand here, right? So 0, 0, 0, 0, 0, 0, and 0, 0, 1. Okay, so you have basically 2 rows of zeros, right? So that means we have only one pivot column, right? So the only thing we know about this eigenvector is that v3, the third component of the eigenvector, is 0. And v1, v2 are arbitrary, independently arbitrary, right? So you could, for example, call v1 r, v2 s, right? You have to use two different arbitrary constants. So now the eigenspace, again corresponding to this eigenvalue, is given by the vectors r, s, and 0. Okay, so that means this can be written as a linear combination of two vectors. In order to extract the basis of the eigenspace, you basically have to write it as a linear combination in R and S. So the easiest way to do it is to split it like that. So you have only R in one side and S on the other one. Pull the scalar out. And so that gives you the basis of the eigenspace. So that's why in this case for lambda 1 equals 2, when we specify the eigenvectors, we don't specify just one of them. We specify two of them because, again, any eigenvector will be just a linear combination of the basis of the eigenspace. All right, so again, the take-home message is that there is not such a thing as the eigenvector. It's an eigenspace, and the eigenvectors provided form the basis. Usually they form the basis of the eigenspace. So I think for lambda 3 we still have dimension 1, right? So let's do this one as well. Lambda 2 equals 3. So in this case, if I subtract 3 from the main diagonal, I get minus 1, 0, 0, 0, minus 1, 0, and then 0, 0, 0. So again, in the reduced echelon form, remember, we notice you have two pivots. So v1, v2 equals 0, because the first two columns are the pivot columns, and v3 is arbitrary. So again, the typical eigenvector will be 0, 0, r, which you can write it in form of a linear combination of 0, 0, 1, right? So that's the basis of the eigenspace. And so let me finish with a very quick example. Even in the 2 by 2 case, you could have dimension 2 for the eigenspace. That's typically when, in the context of differential equations, when the systems are decoupled. So again, a upper and lower diagonal matrix, let's say 2, 0, 0, 2. Okay, so there is a single eigenvalue which is equal to 2. But when you're looking for the corresponding eigenvector, when you subtract 2 from the main diagonal, there is no pivot. So that means any vector is an eigenvector, right? So v1 is arbitrary, v2 is arbitrary. So the eigenspace is the entire R2. So the eigenspace is the entire plane R2, because it's just because any vector is an eigenvector, right? So of course the basis, you can choose any basis, but typically the easiest one is the standard basis 1, 0, 0, 1. So geometrically that means eigenspaces are subspaces, and they can be lines, planes, depending on the case, right? Like for example, in the previous case here, because we are in R3, the eigenspace corresponding to lambda 1 equals 2 will be a plane, right? A plane generated by these two vectors. All right, so that concludes our lesson, and I'll see you next time.